Okay, rates of change. So this is the introduction to calculus. So calculus is a massive part of the rest of the year and a massive part of next year's methods course. So it's about relationships between variables, x and y's, average rates of change. So that's like where if you're working out the average, you add two things together, divide by how many there are. Gradients. So gradient is the steepness of a line. And rates of change, again, so rates of change are where things change over time. So things change over time. And of course, worded problems, solving problems. So how quickly does something change? So we obviously are not going to be able to have a massive classroom discussion now. So things that change quickly, things that change slowly. Things that change quickly might be 100 meters runner. So someone like running the Olympics, 100 meters, very, very quick. Something that changes slowly would be a snail doing the same thing. So things that change quickly, things that change slowly. So we are going to fill some things up with water. So we're going to fill those containers up with water and we're going to pour them in at the same rate. But the height, the rate at which the height of the water goes up into those containers is not going to be linear. This one here will be all the way here, and then it'll get quicker here, won't it? This one here, it'll start off filling up quite slowly, and as it gets narrower and narrower, it'll fill quicker and quicker and quicker. This one here is going to change. This one here is going to change. So we're going to draw a graph against the height against the volume. So let's have a look at this first one. Here's our height, and here's our volume. And we can see during this bit here, it fills up at a constant rate. And this part here is where it's at this level. And this last little bit here, it fills up much quicker. This one here, so here it's filling up slowly, slowly, gets faster, gets faster, gets faster. And when it hits that point, it's probably about there, it gets quicker. This one here, so it starts off, the sort of base is smaller, isn't it? The base gets bigger, 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 then gets smaller again. So it starts off filling up relatively quickly, then it slows down, and then it speeds up again. This one here, you can see it's filling up slower, filling up quicker, and then fills up quicker. So you're going to need to know what the shape of it looks like, and you're just going to make it. It doesn't have to be 100% accurate. You're never going to get these 100% accurate. You just got to get the shape of it approximately right. And this video here is a really good video to watch. We're not going to watch it now because you won't be able to hear anything. But you can play this. Go to Google Classroom, get hold of the PowerPoint, and you can play this video. And this video takes us through this thing, but it takes it, actually does it for you. So this graph here is increasing, isn't it? It's getting, the X values are getting bigger and the Y values are getting bigger. So it says that Y is increasing as X is increasing. We can say the rate of change of Y with respect to X is positive. The rate of change tells us about the slope, the gradient, so sloping upwards. That one's going the other way. So as Y increases, as Y decreases, so as Y gets smaller, X gets bigger. So the rate of change is negative. So this is just from year 7. Positive gradient goes this way, negative gradient goes that way. And of course, a horizontal line will have a 0 gradient. Horizontal line will have a 0 gradient. All right, let's have a look at an example. So here's a graph. Looks to me like it might be a cubic. And we've just drawn it. We're looking at our X values just from -5 to 2. Use the interval notation to tell us what the rate of change, when the rate of change is negative and when the rate of change is positive. So positive means it goes this way, negative means it goes that way. So to me, it's only negative between there and there. So it looks like to me between -3 and 0. So -3 and 0, round brackets. If you think about it, at 3, the gradient is 0. And at 0, the gradient is 0. So we can't use a square bracket because it doesn't include -3, it doesn't include 0. So round gradient. Here, it's in two different bits, isn't it? If you think it's positive here and it's positive here. So the thing union means and, doesn't it? So it's here and here. Now, because the domain is from -5 to 2, and they've used square brackets, at 5, the gradient is still positive. Sorry, the gradient is still positive at 5, isn't it? So that's why we've got the square bracket. And it goes to -3, but we know that at -3, the gradient is 0, so we don't include it. Similarly, at 0, we know the gradient is 0, so we don't include it. 2 is just the end of this particular graph. This is just the way that they've done the domain for this question. We know this goes on forever. So at 2, the gradient is still positive. Constant rate of change. So this is where something changes at the same rate all the time. All the time. It just changes at like time. Change to the constant rate of change. So that will be linear. So if it's constant, it will be linear. And gradient. The gradient of a graph tells us we'll have a constant. If it's a straight line, the gradient will be a constant rate of change. So the rate can be calculated from the graph. So if you've got a graph, you can work out the rate from the graph. And if it's a rule, so like y equals mx plus c, you can just write the rule down. So any function that is linear will have a constant rate of change. So linear is constant. Rate of change is simply the gradient of the graph. So it's just the gradient of the graph. So it could be a positive gradient or a negative gradient. A car travels from Copenhagen to Charlgum. I'm not sure if they're made up places. You might know people who live there. Which is a distance of 150 kilometers in 2 hours, so 120 minutes. Usually they don't tell you that. They just assume you know that. Assuming the car travels at a constant speed, well, we know that that never ever happens, but for mathematically, we're going to assume that it happens. Draw a distance time graph and calculate the speed. So you might already know that speed is a distance divided by time, so you might already work out that it's 75 kilometers an hour. So at 0 time, they've traveled at 0 distance. At 120, 2 hours, they've traveled 150. So when you decide how big your graph needs to be, time needs to go up to 120 minutes and your kilometers need to go up to 150. We don't know any of the points in between, so we just know that 120, it's at 120 minutes, it's traveled 150. So there's our graph. So to work out our rise over our run, we've got our rise, which is 150, divided by our run, which is 120. So it's 5/4 hours, because I think, what have we done? We've done 100, so 150, so it says 5/4 minutes per kilometer. So in order to change that to kilometers an hour, we just times it by 60. And again, because we kind of like, before we even start, we're going, well, 150 kilometers in 2 hours, it's going to be 75 kilometers an hour. So we've already got that. Okay, a little bit more tricky, this one. 3 cars are driven over a 2-kilometer straight track. So drag racing, yeah? They go from point A to point B. Each car travels with a constant speed. It is not a race. So one car, they go at different speeds. The speed of car Y is twice that of car X. The speed of car Z is half that of car X. Illustrate that with a distance time graph. And starting off, assume that car X travels at 1 kilometer in 1 minute. So in a 2-kilometer track, it's going to take 2 minutes, isn't it? So let's start off with car X. So car X, where's car X? Car X takes 2 minutes, so 2 minutes, 120. So there's car X. Assume car X travels at 1 kilometer per minute. So then let's look at the top one. The car of Y is twice that of car X, the speed of car Y. So it's going to take half as long, isn't it? So if that one takes 120, that one's going to take 60. Take half as long. The thing you might get modeled up here is you might get your car Y and car Z modeled up. Speed of car Z is half that of car X. So if it's half, it's going to take twice as long. So it takes 240. So this one here, testing a lot of comprehension. Can you understand what this means? And work out our gradients. Our rises over our run. So there's our gradients. So it's saying that this one is 16 2/3 meters per second. Meters per second. So our units here are meters per second. We think which one's going fastest? That one's going fast, isn't it? So Y is going fastest because it does it quicker. Next is X, and last is Z. So there are many other examples. So petrol consumption. So amount of petrol you use is related to the number of kilometers. Exchange rates for currencies. So here we have the yen against the dollar. So we know that the rates change every day. If you watch the news, it gives you the exchange rates. So that changes. So there are 12 and 12, 24 questions for you to do. Now, this is, like I said, this is just an introduction to calculus. It's going to get a lot more challenging. So make sure you get a really good basis of what's going on here and get all those questions done. Well done.